Hi everybody, I'm Lee, and I wanted to talk a little bit about TCP performance and battling the bloat. And I've got about 45 to 50 minutes of content here that we're going to go over essentially a brief history of TCP, what's made it what it is today, where are we going into the future, and what's the interesting areas of research that is happening around TCP right now. So I'm Lee Finch, and I'm here because I love technology. I do have a Twitter handle, but I don't use it very regularly. If you guys can give me a reason to use it, I will. But I've also got my LinkedIn QR code down there as well. So I'm going to go through an introduction. I'm going to go through some performance basics. What are the things that make TCP perform well or not? Around efficiency and fairness. And then we're going to talk about some buffers, some queues, and some scheduling, what that all means, and then a brief look into some futures around communications and transport control protocols. So some of the learning outcomes we're going to get out of this: who cares about TCP performance? What are the most common TCP performance problems? Application versus transport issues, TCP efficiencies and futures, and metrics that matter. So if we go back to September of 1981, we had the first TCP RFC, which was RFC 793. And when you go through that RFC, there's only two mentions of congestion. They're in relation to timeouts and loss, which are two very different things. And we'll go through that in a little bit more detail. There is some reference to what we call the receive window, which is explicitly in the packets. And we'll talk a little bit about receive windows versus congestion windows as well. So if we go back to the 1980s, we had around 1986 the congestion collapse events. And if you think about the previous slide, I was saying, well, there's no real mention of congestion. That's because there was no congestion window, no slow start, none of these modern things that we have in TCP. So what a few of the researchers in the universities on the west coast of the States saw was the ARPANET dropping from 32 kilobits per second down to 40 bits per second, which is a huge speed reduction by a factor of 1,000. So the operating system, BSD 4.3, why did that behave so badly? And then what did they introduce into BSD 4.4 to make it perform better? Well, what they introduced was 7 new features. And they are round-trip variance estimation, exponential retransmission back-off timers, slow start, aggressive receiver ACK policies, dynamic window sizing, being the congestion window, Carnes clamped retransmission back off, and fast retransmit and fast recovery, which are really important things to understand why, what that original RFC TCP 793 looked like versus what, say, New Reno looked like when Linux kicked off in about 91 rather. So back around that time, before the congestion collapse events, we had, two independent research teams looking at how to solve a particular problem, which was the small window syndrome or the silly window syndrome. And you had some researchers looking at it from a delayed ACK perspective. So they introduced this in BSD 4.2. And instead of acknowledging every packet, they acknowledge every other packet, unless the delayed ACK timer has gone off. And we can actually disable that feature. So rather than ACKing every other packet, we can use a socket option called TCP Quick ACK to introduce the previous behavior where it would ACK every packet. However, John Nagel in 1984 was looking at this from the other end of things. So when we look at a sender sending data and a receiver receiving data, there's the acknowledgement coming back, so that TCP, being a reliable transport protocol, would need that acknowledgement to make sure that the payload got to the receiver. What John Nagel introduced with the Nagel algorithm was the ability, a non-timer based approach to transmission of data from the sender side. And what he introduced was that a full MSS can be sent, or a payload with less than a full MSS can be sent if there's no outstanding data on the wire. So I'm going to explain that a little bit clearer. If a full MSS can be sent, it will. So maximum segment size. However, if there's less than a full segment going out, it can be pushed out without the timer going off, or without a timer, it can be sent. What ended up happening in this situation is a Nagel delayed ACK deadlock can occur, where you have outstanding data on the wire, and it hasn't been acknowledged, and you end up in this situation where the Nagel algorithm will pause until it has an ACK for that outstanding data. So remember, you can send a full MSS, no problem. You can send less than a full MSS if there's no outstanding data on the wire. And Hansung Bay has a really, really good video. I'll put a link in the description to that. That allows you to go through and explore this in a lot more detail. I've also got some packet captures illustrating this. I'll go over on another day. So the way to disable this Nagel algorithm is to use the socket option TCP no delay. And that will allow you to bypass the algorithm. However, I think it was RFC 1122 did specify that you must address the silly window syndrome somehow. And a host should use the Nagel algorithm. The next problem that we have is this global synchronization problem. And the problem is that we have bursty networks, we have tail dropping routers, and we have many, many TCP flows using the same stack. If they fall into a synchronized recovery and back off, what happens is that we might have 1,000 hosts over here, and every host has 10 connections going out. When they all send data at the same time and a router becomes congested, what ends up happening is that the router will typically tail drop. Back in the 1980s, there's ways that we can look around that now, but I'll talk about that in a second. And then because they're all using the same TCP stack over here, they'll all start to back off and transmit at the same time. They end up in this loop of back offs, and that's what we call global synchronization. There's a couple of ways that we address that. One of those is with random early detect. And what that would do would be when a router or device detects that we're about to see congestion occur, it'll randomly drop traffic in the queues. And what that means is that the traffic will, all not synchronize, not fall into a global synchronization of retransmissions, but rather certain flows will start to slow down as a result of the flow control mechanism built into TCP. Remember, we're going to send data out, we're going to send a segment out, and that receiver has to acknowledge that payload has been received. One of the things that we also have is weighted random early detect, and that's an enhancement to random early detect where it will drop flows that it thinks are less prioritized than others. Another approach to this is AQM, or Advanced Queue Management, and I'll talk about that later in the deck. It's a really interesting topic. There's a lot happening in that area as well. So when we look at congestion control, which was introduced in the congestion control and avoidance paper, it introduced, and this was the observations by Van Jacobson et al. Around what we need to do to avoid these congestion collapses. Two of these mechanisms were slow start, and what slow start would do would be starting the congestion window at a multiple of the maximum segment size. So you would specify a value between 1 and 10 that would give you what that congestion window starts at. And what happens is that for every ACK during the slow start phase, so it might start if you've got a maximum segment size of say 1,460, which is typical of an Ethernet network. You would say having a multiple of 10 might be that you've got your 14,600. You would be your initial segment size, or your congestion window rather. And now you would send out your 10 segments, and then for every ACK coming back, effectively what happens is we increase the congestion window by 1, and that means that you're effectively doubling every round trip the amount of payload that's going out across the wire until we reach the SS thresh value, where we move into a congestion avoidance. And a lot of people think like slow start, it has slow in the name. It's actually really fast. And what happens, because you've got that exponential growth, it's going to exponentially climb until it can hit the maximum or the maximum available bandwidth that it can see at that point in time. And then it will back off and then fall into a congestion avoidance phase. And that, instead of increasing it for every ACK we receive, what we end up doing is that we only increase the congestion control window by 1 every round trip. So if the round trip time was, let's say, 70 milliseconds, every 70 milliseconds it would allow for one more segment to go out. So when congestion's detected, the algorithm can do two things. It can change it can do other things as well, but typically they would change the SS thresh value and the congestion window value. The very nature of congestion avoidance, trying to purposefully, get towards the maximum bandwidth available all the time, is we're going to end up with retransmissions. And retransmissions aren't a bad thing; they're actually a really good thing. It's important to note that we're expecting to see retransmissions even in a healthy network, and even more so when you've got a wireless network. And we'll talk a little bit about some of the evolutions of TCP that allow you to use wireless or leaky networks, or leaky pipes rather, a little bit further on. So I've got here just a basic I/O graph from Wireshark, and I've got here the red line, which is the bytes in flight, and I've got the TCP errors. And this is the new Reno algorithm. So originally, and I'll talk a little bit about Tahoe and Reno and then new Reno and so on and so forth, and the differences between them. But what we can see here is that we quickly exponentially skyrocket up to the maximum amount of throughput on that link. And this one was about 250 megabits per second. You can see that once it has more than 250 megabits outstanding on the wire, it'll drop that back. What'll end up happening is we start to see TCP errors. And you can see here that the value actually crashes down at about 14 seconds. And then it tries to go back up again, and then it backs off again. And what's happening at about 20 seconds is I introduced a second flow that you can't see here. But that curve that goes right up when you use the bytes in flight, that's your indicator of what the congestion control window is. Remember that we can't see that. So how do we detect congestion? Well, we detect it from loss and timeouts. We detect it using delay, maybe explicitly using explicit congestion notifications, and I'll talk a little bit about that later. So, how do we detect loss? Kind of the same way. We use timeout, and we can also use a lack of delay variation, and so that's your round trip time variation. But out of order packets is another way that we detect loss. But is that really a good idea if the packet actually got there anyway? Can't we reassemble it at the other end in the right order? And some algorithms allow you to do that better than others. But for the most part, these early algorithms would go, I've got an out of order packet. Is that, that means that I've probably missed something and I'm going to, send a fast retransmit back. So that's your triple duplicate act. We'll go back, and then we've got fast recovery, which I'll talk about in a second, which is the response to that behavior. Then we had selective acknowledgement, which was RFC 2018, and it allows us to selectively acknowledge what data we have received, and it leverages the TCP options. And that means that if you've got timestamps disabled, you can have up to 4 selective acknowledgement, left edge, right edge. If you've got TCP timestamps, you're only going to be able to have 3. But there's a really good paper on this, really good talk from SharkFest 20, which was the virtual event by the CTO, services CTO for Riverbed, John Piddle, and I'll put a link to that as well if you want to go over that. Really, really good talk. So we've got this receive window, and this has always been, the case in right back to the RFC 793, is that we've got this window that the receiver advertises back to the sender and says, hey, I've got this much buffer space. And that number should get up, should become quite large. Originally it was only able to go to 64K. Scaling windows allowed us to do a whole lot more than that, but that's a bit beyond what we're talking about here. But effectively, what will happen is that because we're getting constant advertisements back on how much buffer space is available, or receive window rather, is available, the sender knows how much data can be sent over a single round trip without having to explicitly acknowledge. Sorry, it has to acknowledge that data rather before it can send more. And you can see this in Wireshark. If we send out as much data as available in the receive window, you'll actually see this window full, expert info in Wireshark. If the advertised window, however, drops to 0, that's a completely different problem. That's what we call a zero window event. And that typically happens when the receiving application is not performing very well. It's not reading data off the socket. And effectively what happens is we use up all the receive buffer on the receiver. There's no more, so it's saying, back off, I can't take any more data. And this is that flow control mechanism. But we also have the congestion window. So this describes, from a sender's perspective, how much data can be sent, and it's not directly visible. You can model it or create a graph of it using the bytes in flight. That'll tell you, what the current congestion window is as a multiple of the maximum segment size, or MSS, and it's not directly visible, but it is observable from that system behavior. And it's designed to reach a network equilibrium or fairness. Now, keeping in mind that every single TCP connection that we have will use an independent congestion window. So even if I have my phone having 10 connections to the same server, it's going to, each one of those is going to have its own congestion window, trying to reach some equilibrium or fairness. And there's been, probably the biggest area in TCP development has been those congestion window or congestion control algorithms following the congestion collapse events in the mid-80s. We also have the receive window, which I was talking about just before, and that tells the sender how much data can be received. And, how much data is outstanding on the wire is effectively the lowest of either the receive window or the congestion window, especially during the slow start phase. As I said, the receive window acts as flow control, and it's designed to stop a sender from overwhelming the receiver. This is something that that TCP, rather UDP can't do. You can blast UDP across the wire, and there's no way for the receiver to say, hey, back off. Whereas with TCP, a delay in acknowledging the data will result in a backing off of the sender sending data. We had window scaling implemented, I can't remember the exact revision, but that allowed us to use more than 64K of traffic in one round trip. And it's really important in satellite and global networks where you've got high throughput and you've got high latency. Just remember that zero window and window full are not the same thing. A zero window indicates a problem at the receiver. A window full is flow control to back off. Alrighty, so when we talk about efficiency and fairness, we're looking at equality. Every TCP connection, remember I said that I might have 10 connections off my phone going to the same destination. They're all trying to reach some sort of equality, and some algorithms are better at it than others. And keeping in mind that the algorithm that I might be using might be different to the one you're using, or that somebody else is using. Typically, we're all using Cubic nowadays, and then your content providers are using BBR, which I'll talk about a little bit later on. But there's no mandate to say that we must use the same algorithm when we're talking to each other. But anyway, or even in the same network. We're trying not to starve out other communications, and we're trying to have some sort of equality with unfair traffic like UDP or GRI that have no flow control mechanism in them. And then you've got those stochastic traffic patterns as well. And what that means is that you've got requests of varying length and responses of varying length, and you've got server delays of varying lengths, and you've got multiple people all doing different things at that point in time. So it's not like there's a uniform traffic pattern. And that's why we end up in the situation with, hey, who's using my bandwidth? That you might have at home, where somebody's on Netflix or something to that effect, and everyone else is having a bad day as a result of that. These algorithms require constant feedback, and if there's no feedback at a particular point in time, you can accidentally starve out other traffic. I don't like the term who's using my bandwidth, because I think that technologies like advanced queuing methodologies like Cake and Coddle and whatnot, should be able to resolve that. So some of the challenges that we have is really around equality. And I've got here a fair example, and this is where you might have 3 people sending data at the same time, and the data gets through equally, no problem. But usually what happens is this unfair example here where, one will arrive first, and so you got blue, and then you got yellow, and then you got orange, and you can see here that they're not arriving at the same point in time. So when we talk about efficiency of fairness, we've got our congestion control types, and typically they're one of three. Typically they're a loss algorithm, so they're using things like out-of-order packets or missing packets or timeouts to detect when there's a congestion event. But we also have delay as well. And these are some of the algorithms like Vegas and Westwood and BBR that use latency. They're constantly monitoring the latency of every round trip and looking at delays or changes in that latency to then determine if a link is congested or not. So, we've also got another algorithm here, which I'm going to talk about, which is TCP low priority. And it's designed to soak up bandwidth within a class of traffic when there's no other traffic occurring, and then back off to allow other applications to use that bandwidth as needed. So if we go to the first couple of generations of TCP congestion control algorithms, we started off with fast retransmit and fast recovery, and then we had slow start introduced, and then we had all tolerance for loss and bursts of loss. The first algorithm was really Tahoe, and that was a part of BSD 4.3 Tahoe, and then we had BSD 4.4, which introduced Reno, and it had the fast recovery, allowing you to immediately transmit data on the reception of 3 triple duplicate ACKs. And then we had slow start, which was to ramp up and find that fair share of bandwidth as quickly as possible. And these were written in the late 1980s, well before Tux in 1991. The difference between Reno and New Reno was really just around this tolerance of loss. New Reno was the first algorithm implemented in Linux, and you can see it in tcp_conj.c. You'll see that it's the default algorithm there. It's just, they just call it Reno. It's actually New Reno. Because Linux came along in 1991, this was before, after Tahoe and Reno had been, initially tested in the BSD kernels. So Tux comes on the scene around 1991. I've got here Tux, and I've got here Lux from a Linux conf in Tasmania, Australia. So it's a Tasmanian devil with a beak. And then over here we've got Beastie from FreeBSD, and he came on the scene around 1993, in late 1993. And that Beastie there, he was actually illustrated by John Lasseter, who's famous for a lot of the Pixar movies and a lot of the Studio Ghibli movies that were translated into English. So after that we had Vegas, and Vegas was created in 1994, and it was the first algorithm that I know of that was able to use delay as an indicator of congestion. Some considered it a little bit too fair in that it wouldn't actually consume its fair share of bandwidth. It was implemented in Linux, and it was implemented in FreeBSD, and probably others as well. But those are the two implementations that I've used for my research. And I've got here, Vegas backing off, and this is just bytes in flight, but it's actually, not bytes in flight, it's good put rather. So good put is different to throughput in that it's the amount of data that the application, the receiver, is actually able to read at any particular point in time. And this is different to throughput in that throughput includes headers, it includes retransmissions, and it's everything that actually goes across the wire. When I'm looking at quality of experience for an end user, I care far more about good put than I do about throughput. When every network engineer starts, they think about how do I get as much data, how much throughput I can get at any particular point in time, and that can lead to people incorrectly configuring buffers. This is a really common problem that I'll see. They don't want to drop any packets, and so they'll increase the buffers way too big, and this is that buffer bloat situation. And I'll talk about that later on, but it's just important to use good put as a measure when you're looking at quality of experience. Good put is your metric that you want to use rather than throughput. So if we go to another slight detour here, throughput is how much bandwidth is being consumed, and it includes those protocol overheads, it includes retransmissions, but more throughput is not equal to a better experience. Good put is what we care about from the applications and that quality of experience. Westwood Plus came on the scene around 1999, and it was initially implemented in NS2, which is a network simulator that people use for modeling and simulating protocols. And then we have a modified slow start in that Westwood algorithm, and an adaptive SS thresh as well. And then it was designed to handle long fat networks and leaky pipes. It's known as bandwidth estimation, and it added a low pass filter on the AX stream. It was actually ported to Linux a few years later, around 2003, 2004, and it was actually implemented as Westwood Plus, which had a few enhancements over the original Westwood implementation. So if we talk about long fat networks, think about high bandwidth, high latency, satellite global networks. If you have 100 milliseconds of latency, that means you can have up to 10 turns per second, or 100 milliseconds of round trip rather. A turn is a request response cycle. So think about, get HTTP, 200 OK coming back. That is a request response cycle that we see. And then we have leaky pipes. So where loss is not an indicator of congestion, think about satellite or wireless, where you've got a bit error rate to contend with, or you've also got half duplex connections. That loss is not an indicator of congestion. Then we had TCP Highspeed in, I think that was about 2003, which was RFC 3649. It's used for long fat networks, and it really behaves the same as New Reno until the congestion window reaches 38 segments. What happens there after that is it uses a probability table to ramp up the connection as fast as possible. And what ends up happening after that is once it reaches the end of that table, in the congestion avoidance phase, it'll switch to sending or adding 2 segments to the congestion window every round trip. And that means, unlike New Reno, where it would only add 1 segment per round trip in the congestion avoidance phase, it does ramp up quicker on those really high latency connections. 2003 also saw TCP low priority, and this is one of those odd algorithms where it's not really about efficiency and fairness, but more about soaking the available bandwidth, not to interfere with other traffic. And it was a pretty neat idea. So Cubic, which is the one, we've got 2 algorithms here, BIC and Cubic. And Cubic is the one that everybody's using. I'm using it right now on my laptop. I'm using it on my phone. I'm using it on my watch. It's been implemented everywhere. It's the algorithm that most operating systems, Mac, Linux, Windows, BSD, these guys are all using Cubic nowadays. And it uses 3 phases that it goes through. So it uses a additive increase and multiplicative decrease. It uses the binary search. So once it hits that maximum throughput here, I've got 250 meg here, it'll back off. Instead of backing off 50%, it'll only back off about 1/8. And then it'll try and ramp up again, and it'll use that binary search to work out what the available bandwidth is. And once it reaches that, it's also then going to try and, once it's equalized, it's going to use a max probing to try and work out, can I go higher? It's a really, really cool algorithm. It's still loss-based, but it's really interesting that it's become so popular nowadays. It performs extremely well. BBR is the next one I want to talk about. It came around in the mid-2010s, and it's bottleneck bandwidth and round trip time. And it was designed to address multi-gigabit networks and buffer bloat. So remember I was talking earlier about how some networks will try and add as much buffer as possible to avoid dropping packets. This is what ends up happening is we end up with a situation where the effective round trip time increases because packets are spending more time in the queue. And we call that event buffer bloat. And you end up with the same packet in the queue multiple times as a result of round trip timeouts. Retransmission time is going off, and you end up effectively adding data into the queue. Queue becomes bigger, and it becomes a bad time for everybody. So Google, Neil Cardwell, and Van Jacobson and others built out this BBR, bottleneck bandwidth and round trip time algorithm, and it's used by Google and other content providers. If you're watching this on YouTube, you're being sent traffic using the BBR algorithm, and I believe a lot of the other content providers are using it as well. It's really good for bulk transfer. There's some dispute around fairness in that maybe it consumes too much bandwidth. But I haven't seen enough evidence of that yet. It's mostly some papers that are claiming this. I haven't fully read yet. One of the things that BBR requires is fair queuing, and fair queuing, what it needs from fair queuing specifically is rate pacing, because this algorithm is going to pace instead of dumping the data onto the wire as soon as the window becomes available. I'll talk a little bit about that in a second, in how algorithms like Vegas and Reno and Westwood will effectively dump data onto the wire as soon as it can, and you end up with this really bursty pattern, which is susceptible to tail drop. Rate pacing is a way that we work around that type of problem. So buffers, queues, and scheduling. This is a topic that a lot of people struggle with. So I'm going to start off talking about some buffers and where we see different types of buffers, and then talking about the packet scheduler as well. So any device that sends, receives, or forwards data using TCP has a buffer. Buffers are in-memory constructs, and what we see is that low-end switches and routers have really, really small buffers, which means they can't handle bursts very well. Because memory is relatively expensive, and in these cheaper devices, typically they don't have that. Newer devices have a lot of buffer space available, and that's really important in really fast networks where you might be experiencing microbursts. But is it necessarily a good thing if you use it incorrectly? So big buffers themselves aren't actually bad, but using them incorrectly or carelessly is bad. Forwarding devices don't want to hold packet data for long. They don't want to hold it for forever, and they certainly don't want to exceed the retransmission timeout that sender has for that packet that's in the queue. So on the host itself, we have two types of buffers that we care about. We have the receive buffer, which is provided by the operating system for the application to read from, and it's associated with the receive window. So the receive window cannot extend beyond the receive buffer. Then we have the send buffer, which is for a sender. It has to maintain a copy of all of the data that is unacknowledged on the wire. So if we have a big network, we're going to be able to run data into that send buffer. It has to maintain that until it gets an acknowledgement to say, "Hey, I've got that packet." You can then remove that from that send buffer. So if we look at it just through a diagram, you can see here I've got an application. It's got to write to the send buffer. The data gets sent out over the wire. The receiver reads the application data, deletes it, and the acknowledgement comes back. The sending application sends data back out again. The receiver reads the data. It becomes acknowledged, and it is removed from that sender buffer. So I've recently been working with some container organizations in logistics and whatnot. So I thought I'd throw a container in there. One of the things that applies to forwarding devices is that the faster the throughput, the more memory we need to be able to handle microbursts. Remember that technology does not operate in seconds. You cannot say that I have a 10 megabit connection and I start dropping packets at 4 megabits. Computing and technologies don't operate in seconds. They operate much, much, much smaller than that, depending on the frequency of the CPU. It means that we can effectively saturate a connection very, very quickly. If you've got, say, 1,000 hosts all sending data at the same time in a bursty pattern, you don't necessarily want to, drop half of that traffic because you haven't got enough buffer space. So big isn't bad. It's really about how you use it and how you configure it. Typically, in a forwarding device, you do not want to have more than 2 times the bandwidth delay product. Which is, you can find calculators online to do that. If you can't find one, hit me up. I'll point you in the right direction. But typically 2 times the bandwidth delay product, because that'll roughly equal the retransmission timeout on a sender. And then that'll avoid the situation where you've got packets in the same buffer twice, which you don't want. So when we look at forwarding devices and queues, we've also got things like quality of service that help us prioritize and queue data on a busy interface. And most queues today is statically configured. However, advanced queuing techniques like Cake and Coddle are applying some common sense to it, or some ability to understand which connections are congested and use the flow control mechanism like injecting delay to be able to slow down specific connections that might be experiencing congestion due to a router on the internet somewhere that's congested, that's not impacting all of the connections. Some call quasi managed unfairness. I like that term because effectively you're penalizing or potentially penalizing everything. So big isn't bad, it's how it's used. But what can go wrong? If we queue data for too long, we risk the data being retransmitted again and adding to the existing queue. So think about timeouts. Your retransmission timeout, which is roughly 2 times the round trip time at any point in time. It is a moving average. It's a smooth round trip time. But every time we get a timeout, effectively what's happening is that most algorithms today will reduce the congestion window. And by how much? It could be 1/8, it could be half, depending on the algorithm that you're using. If the queue is too large, we run into FIFO problems where we have the inability to change data that's actually in flight until the queue is back to its mean size. And then remember good put versus throughput. Just because you've got more data on the wire doesn't mean that it's necessarily a better quality of experience. Then we've got scheduling. So advanced queue management. The two that I looked into mostly were FQ Coddle and TCP small queues, which work hand in hand. And FQ Coddle is a way to dynamically introduce delay to certain flows so that you can back off flows that are congested further up the wire, which leads to a better quality of experience. There's a lot of research being done in TCP small queues at the moment. One of the other things that we look at in the packet scheduler, the default one or queuing discipline that we use is P5O fast, at least on Debian and all of the distros that I've checked out. I talked about FQ earlier, fair queue. That introduces some fair queuing and also rate pacing, which I'll talk about in a second. And then we also have rate pacing without fair queuing, which was introduced as part of the TCP output. I can't remember the year that it was introduced, but any modern kernel, you should be able to use rate pacing without necessarily using FQ. And then we've got common applications kept enhanced, which is hierarchical token bucket, less hash collisions, and improved CPU performance over FQ Coddle with a hierarchical token bucket. So AQM strategies can dynamically add delay to individual flows that may be experiencing congestion, and it's designed to work well against buffer bloat. So those routers that you have no control of out on the internet that you have no control of, that's what this works really well with. LibreQuas is an ISP implementation of Cake. It's pretty cool. I'm looking to check that out as well, play with it, do some testing. And TCP small queues, TSQ, was implemented at the socket, can also improve the performance of controlled delay or Coddle. Buffers and, pacing rather, effectively divides the transmission over the whole round trip to avoid burstiness. And that's really valuable in buffer bloat environments where you don't want to send too much data on the wire, impacting effectively the perceived round trip time. And it also allows you, remember, we're thinking in nanoseconds, not in seconds when we're looking at networks and technologies. So rate pacing allows us to spread the load out over the whole the whole round trip time instead of bursting that data as soon as it's available out. And you can see here in a second why that's really bad. I think on the next slide I've got an example of a pacing versus a non-pacing example. So there are two implementations of pacing in the kernel. One is in FQ, the fair queuing discipline, as well as the other one, which was brought in to allow people to use Coddle and AQM simultaneously with BBR as a congestion control algorithm, among other things. And effectively, if you specify the pacing limit in the socket option, Linux will automatically pick up, do I need to do it in TCP output, or do I need to do it in the queuing discipline? So this is a non-pacing example, and I've highlighted packet 52 here because that represents on 100 milliseconds of round trip time, effectively 46 milliseconds I spent not sending any data. And you can see here that as soon as the ACK comes in, I immediately start trying to send data again. And then you end up in the situation where you get this delay. And so there's this effectively like going up steps. We punch all the data out and then we wait. And we punch all the data out and we wait. That's not ideal, because if you've got a bursty network, you've got a whole bunch of dead air time, and then you're susceptible to the available bandwidth at that particular point in time. Whereas if we pace it, we're effectively transmitting data all the time, and we're trying to keep as much data in the air as possible. So we're controlling that output using rate pacing. A couple of things here. I was just at SharkFest a couple of weeks ago, and these are a couple of things that I care about. Delta time is one of those fields that I always have in there because I want to see what the delta time is between the last packet displayed. I always have my bytes in flight so I can understand at any particular point in time how much outstanding data I've got on the wire. And then we've got RTT to ACK, which is my round trip time. You can see here it's very, very predictably about 100 milliseconds, which is the latency of the network that I was testing. You can see here where I've got my pacing versus my non-pacing example. On the left, I've got my pacing example, which you can see here, it's very consistently just streaming data. And you see occasionally it'll pause and hang, and that's just part of TCP flow control. But you can see it's much, much worse on the right-hand side. You can see here there's a lot more breaks in the data, those flat lines. We want to avoid those flat lines as much as we can. So if I was a gambling man, some of the things that I'd expect to see into the future are quick. It's got great adoption in the consumer markets, but really, really slow adoption in the enterprise. And there's some really good reasons for that. Mostly around the level of encryption. It's not as super well documented as TCP is. It's effectively moving the congestion control algorithms into the application layer, which could be a good thing or a bad thing. But because of those things, it is seeing a slow adoption in the enterprise. A lot of firewalls are just blocking it straight up. Multipath TCP, especially in 5G networks, and so you think about automotive, or even just my phone as I drive between one cell to another. Multipath TCP is going to be really valuable in that area. And then AI and TCP. I think we're going to see a lot more of AI in the advanced queuing methodology. You're going to see that's starting to become a really popular thing. So with all of that, I'm going to leave you with it, and I want to thank you for sticking around with me for the last 45 minutes or so. I appreciate it. Any feedback, comments, I'd love to hear about it. I've got those few links, the selective acknowledgements by John Piddle, and the Nagel delayed ACK deadlock, which was done by Hansung Bay. I'll put those in there. Please feel free to reach out to me on LinkedIn, or even just via YouTube. I'd appreciate it. Any feedback, much appreciated. Thank you.